Okay, let's start talking about acids and bases. And this is just going to be a basic overview, and this is why we call it a hodgepodge chapter when it comes to aqueous solutions, because you will go into acids and bases if in more depth if you take Chem 155. So I don't want to go like too far into depth for this, but I do want to cover some information that if you don't take Chem 155 and you do end up taking an organic chem next, that you have some information ahead of time that will help you be successful in that class. So the first thing is that an acid by definition is just a substance that ionizes in water to produce hydrogen ions, and these are more commonly called protons. Um, Whenever hydrogen loses its only electron, because a majority of them only have one proton and electron and no neutrons, we just call them protons at that point. So acids you'll hear will be called like proton donors. So a strong acid is an acid that completely dissociates when in an aqueous solution. So what exactly does that mean? That means that it completely breaks apart. You're going to learn in the next section, in the next class in Chem 155, that you have some acids that don't do that, and they have different properties than the acids that do. So these strong acids almost exactly like ionic compounds in that they completely dissociate when you're in solution. On the other hand, you have these weak acids that don't completely dissociate when in aqueous solutions. Instead, they are just partially dissociated. So when we talked about electrolytes earlier, these would be considered weak electrolytes. If you give a weak acid in solution, you may get your light bulb to turn on, but it wouldn't be as bright as if you had a strong electrolyte. Same thing here. If you have a strong acid and you put it in there, you put your your light bulb in there, light bulb system in there, your light bulb's going to turn on bright. Here it's going to only turn on slightly because there is dissociation, but there's only partial dissociation. A base, on the other hand, is a substance that ionizes in water to produce hydroxide ions, and they accept the hydrogen ions in order to give you essentially water. And so you have two different types of bases. You have a strong base, again, similar, they completely dissociate. So if you have a strong base in solution, and you put that, with your conductivity meter, it's going to read very high. Whereas on the other hand, if you have a weak base in your solution, if you have that, it's going to measure a little bit lower because it only partially dissociates when in an aqueous solution. So there's a couple different definitions that we have that associated with acids and bases. The first is what we talk about Bronsted-Lowry. And essentially what they say is that your acid is your proton donor, which is going to be your hydrogen ion donor, proton donor, and your base is your proton acceptor because it accepts those, it gives off that hydroxide ion, which accepts the hydrogen ion to give you water. Arrhenius bases and Arrhenius acids are a little bit more complicated in that they have longer definitions. That's really the only difference. And that's a substance, when dissolved in water, increases the hydrogen concentration of H plus ions. So that's going to be an acid where they essentially increase your number of hydrogen ions or your number of protons. And a base, by an Arrhenius definition, is something that increases the hydroxide ions in solution. Because remember, water is constantly going back and forth between hydrogen ions and hydroxide ions and water molecules. Lewis acids and bases, whenever you have charges involved, you have your electrons that are being transferred. We talked a little bit about this. We will talk a little bit more at the end of this unit, unit a little bit more in depth. But that's why we have electrolytes, because if you didn't have something that had electricity moving in, charges moving and having those electrons moving, you don't have any electricity generated in a solution. So our Lewis acids and bases are essentially the electron pair acceptors and the electron pair donors. And what that means is when you get an acid, the conjugate, what's going to come out of it is going to be a negatively charged anion. When you have a base, it's going to be a positively charged cation. So here are the strong acids and strong bases that we have. Now, if they are not on this list that's in your thing, remember, all others are weak. So all others are weak acids. Or bases. Okay? So your strong acid, we could also include in here, you can write this, ammonium hydroxide is usually considered a strong base. Even though it's not on this list. So you have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. If it's not one of these 7 acids, it's not a strong acid and it's considered weak. So yes, even our wonderful, joyous hydrofluoric acid, though very dangerous, it is still considered to be a weak acid. Here we have all of our group 1 metals because they all typically are soluble in water, so we consider those if they're hydroxides, including ammonium, because ammonium is mostly soluble in water. So these are all of our strong bases, and then the ones that are that are soluble in water, calcium, strontium, barium, those are considered to be strong bases as well. If they aren't really that soluble in water when it comes to the hydroxides, they're weak bases. And that's because they don't completely dissociate, because if they're not soluble, they stay as a precipitate. So that's a little brief overview of what acids and bases are. But how does acids and bases apply to this class? Well, it's through this idea of titrations, which you will do a similar titration, not exactly the same because we don't send burettes home in your packet, in your lab pack, but you'll do it with a graduated cylinder and it's the same idea. But titrations, these are essential. If you want to go into any form of industry where you are doing chemical testing, this is what you will do 95% of the time. Because I can't tell you how many titrations I've done, because of how many times that I've had to, do this to determine different purities of substances. Everything you can think of, we titrated to determine it. So we mostly do this, and I always introduce this in acids and bases, because a lot of times what you're using in the titration is an acid or a base, because most of our indicators are based off of pH. Which we'll talk about all those things in a minute. But a titration can be done without an acid or base. It's just not very common. So a titration is an analytical method for determining the concentration of solute in a sample by reacting the solute with a solution of known concentration. So you essentially want to almost it's almost like you're doing a precipitation reaction, but you're not doing a precipitation reaction. So your titrant is what you're going to put into your burette, or what you're going to drop into your graduated cylinder when you're trying to determine your amount of substance for that specific situation. So this is going to be the standard solution that you add to the sample. Typically, someone has gone through and done three times where they've standardized it, and that allows for you to say confidently it is such and such concentration. And analyte is the substance that you are looking to determine. So when we talk about analyte, it's really just whatever is in solution. So if we're looking to determine, the concentration of a hydrochloric acid solution, we are going to do this using, maybe sodium hydroxide or something like that. So the hydrochloric acid, HCl, is your analyte. And finally, what happens here is what we call a neutralization reaction. And this is actually another part of our double displacements. Remember, we had double displacements in precipitation reactions? Well, the other way we can kind of see these is in neutralization reactions. And what neutralization reactions are is that when you have an acid that reacts with a base, you form a salt and water at the end. Okay, and so that's what a neutralization reaction is. So what happens in a stoichiometric titration is that you get two different points that occur. You have your equivalence point, which is the point at which the stoichiometric quantities are exactly equivalent. And you have an endpoint, and that's where you start seeing a titration or a color change because you've reacted all of the sample in the reaction. So if we looked at page 168 and you have your wonderful thing here, remember, it looks something like this. And we're typically basing this off of pH. So as you add more volume of your titrant, so that's titrant volume here, you're going to see that you have your equivalence point, which is where everything's exactly the center. And then this point here is considered to be your end point because that's going to be the point at which you know that you've reacted with everything. And it starts, instead of staying at that neutral pH of 7, it goes one way or the other depending on what type of titration you're doing. Okay. So your titration apparatus looks like so. You guys won't be doing this exactly. Your burette will be a dropper, and you'll be using your graduated cylinder to tell your numbers. But this is what we do if you were in the lab and in person on campus. This is what we would do. We would take our burette and stand here. We would have a burette clamp. We would put our burette here. We would have our analyte, a certain amount of an unknown concentration, so whatever much it says to do in our lab manual or whatever it says to do in our lab, experiment or whatever we're doing in the field. We follow the directions to do that, and then we take care of that. You have your titrant, and what you're doing is that you're going to just be putting it through a stopcock, and what you're going to do is you're going to let it gently go down, slowly, until you start to see that your indicator has changed colors. So here it changed to a nice little color of pink. When it does that, and it's a very light pink for this situation, for this specific indicator, then you're going to take your final reading. So before you start anything, you take your initial reading, you take your final reading, okay, and your titrant volume is the difference between the two. And so if you know your volume, so if you know your volume, you know your molarity, you can solve for moles. And that's how a titration works. So indicator, that's going to be something that, that's going to be a chemical that changes colors when the endpoint is reached. So, basically, these are mostly dependent upon pH. So depending on where you want your pH change to occur will be determines what type of indicator you use. One of the most common types of indicators is phenolphthalein. So phenolphthalein is clear below 8 pH, and then it turns pink. And that is the one you will be using in your lab. But these other ones, methyl red, phenol red, bromothymol blue, methyl orange, bromocrescal green. Again, you just look up your specifications, what color you're looking to change for. Methyl red will turn to like an orange color. This will turn to a red. And they're very distinctive. Like they change, like you can tell the colors that will change. And so the idea is that you add these indicators, and when you start to see your color change at a specific pH, whatever your pH is for your overall reaction that you want to occur, that is going to be your indicator. That's the indicator you choose to use. So if I want to titrate with sodium hydroxide, I'm probably going to pick phenolphthalein versus methyl orange, which I would probably use if I was titrating with hydrochloric acid. Okay, so solving titration problems. And so these are just examples of what could be given to you for solving titration problems. So, determine the moles of titrant added to your sample, convert to moles of analyte using the stoichiometry map, and then determine the concentration using your molarity equation. So our first example here, we want to determine the concentration of a 200 milliliter sample of HCl if 50.10 milliliters of 0.1 molar sodium hydroxide is required to completely neutralize the sample. So we're going to first determine our moles of our sodium hydroxide. So we're going to determine moles of sodium hydroxide. And to do that, we have to use our molarity equation, which is going to be moles over liter. But if you remember, if we're solving for moles, it's really just molarity times liters. And so we have our 0.100 and we're going to multiply that by, we have to convert this, so it'd be 0.05010. So our moles of NaOH should be should be 0.00501 moles. Now, because this is a 1-to-1 ratio, if this is our moles of NaOH, that's going to be the same for our moles of HCl. And that's why we like to pick typically something that has a 1-to-1 ratio, because then we can use whatever moles we have of our titrant is going to be our moles of of our analyte. And so when we do that, we're then going to look at the total volume. And so the total volume is going to be our volume of our sample. And that's going to be 200 milliliters. So now we have, if we're going to determine our concentration, we have our moles divided by our liters. And we're going to round to 3 sig figs, because that's how many we started with at the least. And so that's 0.0251 molarity for HCl. Okay, now let's determine the concentration of a 100 milliliter acetic acid sample, and that's our acetic acid, used in apple cider vinegar if 48.60 milliliters of 1.88 molar sodium hydroxide is required to completely neutralize the acetic acid sample. And so what you're going to do is you're going to put in your number, you're going to solve for your moles of your sodium hydroxide. So moles is equal to molarity times liter, which is going to be 1.885 times 0.04860. So your moles of sodium hydroxide is going to equal 0.009 moles of NaOH. And remember, because this is 1-to-1, then our moles of CH3COOH, or acetic acid, is going to equal the same. And we're going to take our total molarity, our total milliliters from our original sample. And so to determine our molarity, we get 0.0916 divided by 0.100. And so we should get 0.916 m of our solution. Okay, And so the last one you can figure out on your own, and I will post the answer on Canvas. So let's talk a little bit about pH and pOH. So pH, how do you calculate for pH? So when you have a acid of any sort, even though it's a strong acid, it still produces a smaller amount of overall hydrogen ion concentration. So because of that, we have to express it as essentially pH. And so what we're going to do is we're going to round to 1 decimal place unless otherwise noted. So our formula for pH is just going to be the negative log, which is why you need to have at least a scientific calculator out right now, the negative log of H plus 1, so of our hydrogen ion concentration. The same thing goes for our hydroxide ions. Again, when you if you have a strong concentration of hydroxide ions, or if you have a strong base, you're still only going to get a molar concentration that's a little bit low. And so because of that, we need to express it more as a pOH in a general term. And so, again, same situation. We're going to do that. What you want to do then is you want to round to at least you want to use this equation here and round to 1 decimal place. So for our example, we have pOH is equal to the negative log of the concentration of hydroxide ions. So if we wanted to relate pH and pOH, we are going to relate it by adding them up to 14. So let's do a little practice. So if anybody wants to know where the log button is, it's typically below your second button. It says log on your calculator. That's always log base 10, and that's what we're concerned with here. So we want to find the pH of a solution that has a hydrogen ion concentration of 3.25 times 10 to the negative 3. So if I have a hydrogen ion concentration of this, I want to find my pH. I write my equation out. pH is equal to the negative log of your hydrogen ion concentration. And so my pH is going to equal negative log of 3.25 times 10 to the negative 3. And then I put it into my calculator. Now, you don't need any units on these numbers because when we're looking at pH, it's just a relative value. And so there's no units required. So you should get a pH, and we're going to round to 1 decimal place, pH of 2.5. Okay, now let's find the pOH of a solution. So if we're looking for pOH, it's just the negative log of our concentration of hydroxide ions. And so if we want to find the pOH of a solution that has an hydroxide ion concentration of 4.25 times 10 to the negative 6 molar, we're going to take our pOH and substitute that in. So again, remember, you can always use that E value to do the 10 to the negative 6. And so my pOH is 5.4. Now, what if I want to find the pH of a solution that has an OH concentration of 2.25 times 10 to the negative 2 molar? So what you're going to do here is you're going to solve for your pOH first and then use your relating pH and OH question to determine your overall pH. So that's going to be negative log of your hydroxide ion concentration. So your POH is going to equal negative log of 2.25 times 10 to the negative second. And so that should give you a POH of 1.7 or 1.6, sorry, 1.6. So our pH plus our POH is going to equal 14. So pH is just going to equal 14 minus POH. And so when you take 14 minus 1.6, you should get 12.4 for your pH. Okay, so why don't you do the next three on your own, and I will post the answers on this slide for you to see. The last thing we're going to talk about for this unit is just going to be oxidation and reduction reactions. We call them redox reactions. But when we talk about this, we're just talking about determining really oxidation states. We're not determining oxidation, whether something has been oxidized or reduced, because you will do that a little bit more in your Chem 155 class. So, the oxidation state of an element is a positive or negative whole number dependent upon the number of electrons gained or lost. And so what that means essentially is that when we've been determining the charges on our elements for our nomenclature, we've actually just been determining the oxidation state. I just haven't been calling it that because, again, most of the time when it comes to the oxidation state, we're either looking at an anion and a cation. And sometimes those cations, you have to be able to determine what the oxidation states are. And sometimes, if you have a polyatomic ion, we just give it a general for the overall ion rather than individual elements within that part. And so there are two major situations in which you have to determine the oxidation states, and that's going to be your transition metals. We've already been doing that with reverse crisscross. I'll show you another way in which you can determine the oxidation state on a transition metal here in a minute. And polyatomic ions. These are questions that you might see on your multiple choice questions of your exam. So the first thing we're going to do here is determine the oxidation state for chromium, CrCl3. Okay, so let's go ahead and determine the oxidation state for chromium. So what we've done before is we've done the reverse crisscross method. We have CrCl3, we reverse crisscross, and you get Cr plus 3, Cl minus 1. So your charge has to be plus 3 because chlorine gets a minus 1 charge. That's what we did before. If that was a little bit confusing for you, here's another way that you could do this, and this is how we're going to do it for the polyatomic ions. So we have chromium and we have chlorine. We don't know what the charge is on chromium, so we're just going to call that for right now X. And we know that our charge on chlorine is going to be a minus 1 because it's in group 17. So when we put this into our equation, because it's Cl3, we have to multiply our charge by 3. And that has to add up to 0. So you essentially get X minus 3 is equal to 0. X equals 3. And so my oxidation state is 3 for chromium. So that works, like I said, either way works for the transition metals, but what's more important is to talk about is the oxidation states when you have non-transition metals or when you have polyatomic ions. And so here's our example. We want to know what the sulfur is, so that's the S in CaSO4. And so we have Ca, calcium's in group 2, so that's going to get a +2 charge. S is what we don't know. And we have O4. O always gets a -2 charge, so if we take it times 4, that'll give us a -8 charge. So we have 2 plus x minus 8 is equal to 0. So you get x minus 6 is equal to 0, x equals 6. So my charge on sulfur here is going to be +6. And that's my oxidation state. Now if I wanted to do it for nitrogen, so we have K, which gives us a +1 charge. It's in group 1. And I don't know in this situation, because oxygen always gets a -2 charge. And just remember, oxygen always gets a -2 charge, in case I haven't said it enough times in this course. Oxygen will always get a -2 charge. And because we have 3 oxygens, we have to multiply that by 3 to give us a -6. So we have 1 plus x minus 6 is equal to 0. X minus 5 is equal to 0, so x is going to equal +5, and that's our charge on nitrogen. So the next two, why don't you do, and I will resume the video with your answers. Okay, so you should have gotten for manganese, this would be +5, as you can see on my little slide here. And for copper, you should have gotten a +2. Now let's just talk about just some definitions about oxidation reduction so that when you see them in your next course, you are familiar with them. So the first one is oxidation. And so this is a chemical change in which an element loses electrons. So when it's oxidized, it's losing electrons. On the other hand, when you have a reduction reaction, this is where whichever element is reduced is going to be the one that gains the electrons. If you have an oxidizing agent, on the other hand, that's going to be that's essentially the reactant that is reduced. So if your oxidizing agent is the reactant that's reduced, it accepts the electrons. And your reducing agent is whatever's oxidized. It's going to be giving up the electrons in a redox reaction. So now you've gone over this, go ahead and complete your quizzes on Unit 8.